Hello, in this video we are going to discuss about the topic combinatorics. Let me introduce you to my team
My name is Shivam Kansagar.
I'm Prakash Mathur.
I am Karthik Dangi.
and myself Krish Gulabani. Let's begin. The topics we are going to discuss are first the introduction, second application, third problem and its solution, and fourth commercialization. Let me introduce you to the word combinatorics. Combinatorics, also called combinatorial mathematics, the field of mathematics concerned with the problems of selection, arrangement, and operation within a finite or discrete system. What are the applications of combinatorics? Combinatorics has many applications in the fields of mathematics, and some of them are factorials, permutations, combination, combinatorics and Pascal's triangle, patterns within the triangle, combinatorics and probability, graph theory, design theory, finite geometry, and order theory. We will discuss few of them in the upcoming slides.
Okay, so now I am going to discuss some problems related to combinatorics. So now let us first discuss what is factorial by going through a problem. So the problem is, in a classroom there are three peoples and three chairs standing in a row. So in how many ways or different orders can the people sit on these chairs? As we can see, the different peoples are represented by three different colors of chairs as shown in the figure. So we can see that there are six different possible orders. But we can notice that the number of possible orders increases very quickly as the number of people increases. Like for example, if there are six peoples, then there are 720 different possibilities and it becomes impractical to list them all. Instead of all this lengthy calculations, we want a simple formula that tells us how many orders are there for n peoples to sit on n chairs. Now suppose if we have 4 chairs and we want to place 4 peoples on them. So there are 4 people who could sit on the first chair, then there are 3 people who could sit on the second chair. There are 2 choices for the third chair and only one choice will be left for the final chair. So there are total 4 into 3 into 2, that is 24 possibilities, or we can represent it at 4 factorial. That is 4 factorial is equal to 4 into 3 into 2 into 1. So to simplify all this, mathematicians use a term called factorial.
So I'm going to tell you about permutations and combinations. Strategy above expected us to have similar number of students as seats to sit on. However, what occurs if there are insufficient seats? What number of various conceivable outcomes are there for any two of three understudies to sit on two seats? Note that one will be left standing, which we don't need to incorporate when posting conceivable outcomes. Allow us to begin again by posting all prospects. To track down a straightforward recipe like the one above, we can consider the big picture in a fundamentally the same as way. Indistinct in all out there are potential outcomes. Again, we should consider summing up this. We start like we would with factorials. However, we stop before we arrive at one. Indeed, we stop when we arrive at the number of students without seats. While putting 7 students on 3 seats, there are following outcomes. Since the 4 into 3 into 2 into 1 will drop one another, again there is a more straightforward documentation for this. 7p3. In the event that we need to put n objects in m situations, there are npm equals n factorial upon n minus m factorial possibilities. The p stands for permutations. Since we are tallying the number of permutations of objects on the off chance that m and n are something similar, we have npn, n factorial upon n minus n factorial, which is n factorial upon 0 factorial. To figure out this, we characterize 0 factorial equals 1. Presently, npn equals n factorial, as we would anticipate from our answer for the primary issue. Suppose I'm a penny pincher and can't bear the cost of independent gold, silver or bronze awards. Indeed, I can just bear the cost of void metal jars. What number of ways would I be able to give 3 metal jars to 8 individuals? All things considered, for this situation, the request we pick individuals doesn't make any difference. On the off chance that I give a can to Alice, Bob, and Charlie, it's equivalent to providing Charlie, Alice, and afterward Bob. In any case, they are similarly baffled. This raises a fascinating point. We have a few redundancies here. Alice Bob Charlie equals Charlie Bob Alice. Briefly, how about we simply sort out the number of ways we can revamp 3 individuals? All things considered, we have 3 options for the primary individual, 2 for the second, and just 1 for the last. So we have 3 into 2 into 1 approaches to remastermind 3 individuals. In the event that you have n individuals and you need to know the number of courses of action there are for every one of them, it's simply n factorial. Thus, on the off chance that we have 3 metal jars to part with, there are 3 factorial, or then again 6 varieties for each decision we pick. In the event that we need to sort out the number of combinations we have, we simply make every one of the permutations and gap by every one of the redundancies. For our situations, we get 336 permutations from a higher place, and we partition by the 6 redundancies for every stage, and we get 336 divided by 6, which equals 56.
Combinatorics and Pascal's triangle. Given, find first the coefficient of the term, second the sum of the coefficients. Solution. You need to find the sixth number. Remember, the first number in each row is considered the zeroth number of the 10th row in Pascal's triangle. The 10th row is 1, 10, 45, 120, 210, 252, 210, 120, 45, 10, and 1. Thus, the coefficient is the sixth number in the row, or 210. This can also be found using binomial theorem. Combinatorics and probability. Here is an example. 4 children called alpha, beta, gamma, and delta sits randomly on the fourth chair. What is the probability that A sits on the first chair? Solution. We have already shown that in total there are 24 ways to sit on 4 chairs. If you look back at our solution, you will also find that alpha sits on the first chair in 6 of the cases. Therefore, probability of alpha sits on the first chair is equal to number of outcomes where alpha sits on the first chair divided by total number of possible outcomes. This gives 6 by 24, which is equal to 1 by 4.
So now I am going to tell how we can commercialize our project. There are many different ways in which we can commercialize our project. Like permutations are frequently used in communication networks that requires secure transfer of information, which drives development in cryptography and network security. This area has recently become particularly significant because of the increased use of internet information transfers. Cryptography includes encryption and decryption. Encryption process involves manipulation of sequence of codes such as digits, characters, and words. Hence, they are closely related to combinatorics, possibly with intelligent encryption process. For example, one common type of encryption process is interchanging, that is, permuting parts of a sequence. Thank you for watching this video.